Assalamu alaikum. Welcome to the lecture 4 of Unit First. Characteristics of switch. In previous lectures, we have discussed that power semiconductor devices behave like electronic switches, which means that it has two states. One is on state and another is off state. Firstly, I am going to explain you ideal switch. An ideal switch is that switch which possesses current I is equal to 0 and infinite voltage during turn off, which means that power during turn off, which is the multiple of voltage and current, is equal to 0. Or you can say that P off is equal to 0. Similarly, during turn on, current across the switch is infinite and the voltage across the switch is 0. Or we can say power during the power during turn on of switch is equal to 0. Or we can say that when switch is off, I is equal to 0 and voltage will be infinite from minus infinity to plus infinity, and same which implies that power, which is the multiple of voltage and current, will be equal to 0 as current I is equal to 0. Similarly, when the switch is on, V is equal to 0 and current will be some infinite value, that is from, it can be written as minus infinity to plus infinity, which implies that power P of is equal to 0 as voltage, which is the power, which is the multiple of voltage and current, and here V is equal to 0. That means P is equal to 0. Now let us explain the graph of ideal switch. If the switch is initially turned on, then there will be some amount of current which is represented by ID, and the voltage across the switch is represented will be 0. When the switch is turned off, this ID reduces to 0 instantly. That means this ID reduces from this some finite value to this 0 instantly without any delay, and the voltage suddenly increases to some, and the voltage, and this voltage, which is firstly during turn on 0, this suddenly increases to some finite value Vd. This transition or switching period Ts, this is represented by Ts. This transition from on to off and off to on, this is represented by Ts, is 0 as the change of state is instantaneous, so switching losses across this period will also be 0. Or we can say that power loss across the on state power loss across the on state is equal to 0, power loss across the off state is equal to 0, or we can say that conduction losses during the on, conduction losses during the off, and switching losses during this Ts is equal to 0 interval is equal to 0. Now let us consider the practical switch. In practical switch, when switch is closed, that means when switch is turned on, the current will flow, and that current has some finite value. That means it has some range from I minimum to I maximum, and also there will be some voltage drop across the switch. Means that means this voltage drop will not be equal to 0 as in case of ideal switch. It will be it will be some finite value but not equal to 0. Similarly, during turning off of a switch, of a practical switch, there will be finite voltage from V minimum. That means V off will be its range will be from V minimum to V maximum, and there will be some current across the switch. while as in case of ideal case, the current across the switch during off period is zero, but here the current I off is not equal to zero during the practical case. Or we can say that both during the on of practical switch or off of practical switch, we have some power losses, and that power loss we can say power on losses or power off losses is equal to some finite value. Now let's explain this graph. If the switch is turned initially on, that means during the practical case, then there will be some finite value of current during the on period, and similarly the voltage across this period will not be equal to zero, but it will be some finite value across the finite value across this on period. If the switch is turned off, that means here the switching, that is from on to off, is not instant. It takes some time, and that time is represented here by T off and T on. That means time taken by the switch from on steady state value to off state value, that you call as T off, and time taken by the switch to turn from off steady state value to on steady state value, that you call as turning on off, T on off, which is represented by small t off and small t on. Both these represent the switching loss periods, and the power loss across the switches are represented by some value. That means there will be some values across the switching period T off, and there will be some switching losses across this period T on. Similarly, here if this is the current waveform, this is the voltage, and this is the multiple of current and voltage, that means that is the power. During on there will be some finite value of current. Here the voltage will not be equal to zero, but something more than zero. During off, and it changes its state from on to off, the current will decrease from finite value to some smaller value but not equal to zero, and the voltage will increase from some smaller value to the higher value, some finite value. Similarly, if we have to change the state again from off state to on state, the current will rise from smaller value to higher value, and the voltage will rise from higher value to that smaller value. There will be power loss across this conduction on period, there will be power loss across this conduction off period, and there will be switching losses across the both switching period, that is T off and T on. That means the switching time is equal to T on plus, this means switching time will be equal to T on plus T off. Normally the switching losses are greater than the conduction losses. Now we are discussing the first power semiconductor device, that is power diode. As you have already studied in analog electronics, the signal diode, um, the voltage withstanding capability of signal diode is plus minus 15 volt, while as the voltage withstanding capability of the power diode is in kilovolts. Similarly, the current capability of signal diode is from microampere to milliampere, while as in power diode, the current carrying capability is from ampere to kiloampere. Similarly, the power capacity of signal diode is from megawatt to some watts, while as the power handling capability of power diode is from watts to some kilowatts. This difference in rating this difference in rating is due to some constructional change. The
Layer is
applications of
slightly
power
to
diode, that
N
means
negative
this
layer.
power diode, they can be used as freewheeling diode for AC to DC conversion and for recovery of trapped energy. Like other semiconductor devices, this PN junction forms the basic building block of this power diode. This PN junction is formed when P-type material or semiconductor is brought in physical contact with N-type material. Here, P-type material has greater concentration of holes and N-type of material has more concentration of electrons. In P region, we know that holes are majority carriers and electrons are minority carriers. Similarly, in N region, the electrons are majority carriers, while as holes are minority carriers. Doping densities in P and N type semiconductors may be different. For example, in this power diode, here it's a three-layer device, and the outer layer we represent by P positive. That means the P positive, it means that it's highly doped. Similarly, the outer layer, this third layer, we call that as N positive. That means this is also highly doped. And this inner layer is N negative. That means the doping density of this inner layer is less as compared to outer two layers. As we know that when P and N type material is brought in physical contact, depletion layer is formed, and this depletion layer is due to the diffusion of charge carriers, and hence electric field is established across this junction, which stops further diffusion. Width of this depletion layer is of the order of 5 into 10 raised power minus 4 millimeter, and hence there is a potential difference, and there is a potential difference of 0.7 volt across depletion region in silicon and 0.3 volt across depletion region in germanium, and this potential difference across depletion layer is called barrier potential. If the biasing is applied, that means if an external voltage is applied across this anode cathode terminals, during forward biasing means when P is connected to the positive of the battery and N is connected to the negative of the battery, the width of the depletion layer gets reduced. While as during reverse biasing, that means during reverse biasing, if P is connected to the N negative terminal of the battery and N is connected to the positive of the battery, the width of the depletion layer gets increased. Also, we should keep in mind that a rise in junction temperature also decreases the width of depletion layer. Uh, as the barrier potential depends on width of the depletion layer, the barrier potential decreases with rise in junction temperature. So it should be kept in mind that a junction with lightly doped layer on its one side requires large breakdown voltage, and a junction with highly doped layers on its both sides requires low breakdown voltage. The first figure, this represents the circuit symbol for the power diode. The circuit symbol for this power diode is same as that of a signal diode. The structure, the second diagram, this represents the structure. Basically, this power diode, the only difference between the signal diode and the power diode is this inner layer, this inner lightly doped layer. This layer is absent in that signal diode, and this negative layer is the basic structural feature that is not found in that signal diode. um, uh, that means it's a three layer. This P is represented by P positive, that means this is highly doped. This N is represented by N positive, that means this is highly doped, and this inner layer is N negative, that means this layer is lightly doped as compared to the outer two layers. The this Because of this N negative, because of this N negative layer, the main function, there will be one depletion layer across this P positive and this inner layer, that is P positive N negative. The junction here formed is P positive and negative junction, and the main function of this N negative layer is to absorb the depletion layer of the reverse biased P plus N negative junction, or we can say this junction J1. The main function of this inner layer is to absorb the depletion layer of the reverse biased P positive and negative junction or junction J1. Or we can say greater the breakdown voltage, greater the breakdown voltage, more will be the thickness and negative thickness of this inner layer. Due to this n negative layer, due to this inner layer, during the forward current, it adds to some more resistance. So proper power dissipation is required. So cooling arrangements are essential for power diodes. Now, the IV characteristics of power diode. This is the third diagram that represents the IV characteristics of a power diode. If this anode, if this diode, if anode is made positive with respect to cathode, that means if this diode is forward biased, then initially no current flows until that depletion layer is removed. Same is the case with single diode as well as the power diode. In case of signal diode, if anode is made positive with respect to cathode, firstly initially no current flows until that depletion layer is removed, and then the forward current flows. Firstly it flows exponentially in case of signal diode, and then it flows linearly, while as in case of power diode, if we are increasing this forward voltage, if we are increasing the forward voltage, firstly no current flows until that depletion layer across that junction G1, yeah, or you can say that junction P positive and negative is removed. After that, when the depletion layer is removed, the forward current will varies. This forward current varies linearly with that forward voltage. Here in case of signal diode, this cut-in potential, or which you also called as that which you also call that threshold voltage, that is 0.3 volt for silicon and 0.7 volt for germanium, while as in this case, in power diode, this threshold voltage is equal to 0.8 volt to 1 volt. Now the reverse characteristics, that means if this cathode is made positive with respect to anode, that means if this diode is reverse biased, a small amount of reverse, or which you call as leakage current, flows as this diode, small amount of leakage current, and this diode behaves as open circuit, or you can say the diode is turned off. But this diode has some voltage withstand capability. With That means with further increase in voltage, the time can came when you are increasing that reverse voltage. If we are increasing the reverse voltage, small leakage current flows. But if we are increasing the reverse voltage, if we are increasing the reverse voltage beyond this breakdown voltage, junction breakdown occurs. Basically avalanche breakdown occurs, resulting in the large amount of current. This may destroy the diode because of the excessive power loss across this junction. So it should be kept in mind that the peak inverse voltage, this peak inverse voltage is the largest reverse voltage which a diode may be subjected during its working. This peak inverse voltage should be less than this breakdown voltage, else the diode junction may gets destroyed, and the power losses will be very very high due to the excessive heating across due to the excessive heating across this junction. If we are This is now the next diagram is the linear approximation and the ideal characteristics of a diode. For the ideal diode, this voltage during forward current, the voltage drops, or that is 0.8 to 1 volt for power diode, that's considered as equal to 0. The leak during And this forward current is treated as infinity. The leakage current is treat is equal to 0, and this reverse voltage is considered as infinity. Now let us explain this diagram. Here this represents the steady state. That means up to this interval, this dotted line, this represents the on state and this represents the off state. Here this is basically we know that during on state there will be some steady state current, that is forward current, and that's why it's represented by IF. And after the turning on off, because from this interval the turning off of a diode occurs. That means this forward current, because during off current will be 0 and voltage will be maximum. That means during this off interval the current starts decaying. Now at turn on, the diode is basically considered as an ideal switch because it turns on rapidly compared to the transients in the power circuit. However, at turn off, the diode current reverses. Firstly it becomes equal to 0, and then after that it reverses for a small period of time, that is called the reverse recovery time. That is designated by TRR, which itself is divided into two intervals, that is T2 and T3. This reverse recovery time uh, basically um, after the forward current decays to 0, the diode continues to conduct in this reverse direction because of the presence of stored charge. This QR represents the charge stored under this area curve, under this current curve, because the area under this current curve represents the charge. That means this reverse recovery time is defined as a time between the instant when the forward current becomes equal to 0, that is from this interval till this till this current becomes 0, till this current decays to 25, or we can say after that reverse. This is when the forward current becomes equal to 0, then this reverse current flows till it reaches its maximum, that is called IRM, and after that it starts decaying till it reaches 25% of that reverse current. That means from this interval where the IF becomes 0 to this interval, that means at the end of this interval T2, where the IR, that means this reverse current, reaches its maximum value, that is designated by RM. Basically this time interval represents the charge stored in the depletion layer. That means during this time interval, charge stored in the depletion layer is removed. And similarly, time TB is measured from the instant when the current reaches from its peak value to 0.25. That means 25% of its peak value. This During this interval, charge from the semiconductor layers is removed. Um, this reverse recovery time determines the switching frequency of the circuit, and therefore it's very important to calculate this reverse recovery time. Mm. The same is represented here in this diagram. This IF represents the interval. This is the steady state forward current. From this interval, the off state occurs and the current becomes equal to 0, but the current still starts flowing until this reverse current reaches its 25% of its peak value. This is because of the two factors. In the previous diagram, we are representing this by T2 and T3. Now in this diagram, I am representing this by T2, TA and TB. And that means to calculate the charge under this curve, we can represent this represents the triangle. This charge can be written as QR is equal to 1 by 2. That is the base, which is equal to IR base into altitude. That is TRR. This is the base, and the altitude is equal to IRM. That means QR is equal to 1 by 2. This is the base. This is the altitude. Or we can write, that means this slope, This is the slope di by dt that can be represented as, that is the perpendicular upon base, that means IRM divided by TA. Here in this QR, this TRR is basically equal to TA plus TB, charge time taken during the charge. This is that interval. In which the charge is stored in the depletion layer, and this is that interval in which the charge is stored in the outer semiconductor layers. This slope is di by dt is equal to IRM into TA, or we can write this as IRM is equal to di by dt into TA. Here this TP upon TA is represented as softness factor. This factor is a measure of the voltage transients that occur during the time diode recovers. Its usual value is unity, and this indicates low oscillatory reverse recovery process. For example, if here TB is equal to STA, if we put this TB is equal to STA in this equation, we can write that TR in this equation, TRR is equal to TA plus STA, that is equal to 1 plus STA. Uh, Putting this, if we put this value in this IRM, this will be equal to di by dt into Ta, which is equal to TRR upon 1 plus S. This is the equation first, or we can say that this QR is equal to 1 by 2. If we put this value in this equation, that is equal to di by dt TRR ka square divided by 1 plus S. If we assume that TB equal to 0, that means the charge carriers in the depletion layer, there is no charge carrier in the depletion layer. That means after this peak value, the time taken by this reverse current to become zero uh, is very less. Or we can represent that TB is equal to 0, or we can say that S is equal to 0, and this diode is called as fast recovery diode. In this, if we put this value in this QR will be equal to 1 by 2 di by dt TRR ka square. Diodes are classified according to their reverse recovery characteristics. The different types of power diodes include standard recovery diodes, fast recovery diodes, Schottky diodes, and silicon carbide diodes. Standard recovery diodes. These diodes have reverse recovery time of approximately 25 microseconds. The leakage current here in the off state is of the order of few microamperes. These have lower on state voltage drop. These are available with ratings of several kilovolts to kiloamperes. These are typically used in rectifiers at power frequencies that's at 50 Hz or 60 Hz. Fast recovery diodes. Fast recovery diodes. These diodes have low reverse recovery time of approximately less or equal to 5 microseconds. These have relatively higher on-state voltage drop. These are typically used in DC to DC converters and inverters operating at higher frequencies as freewheeling diodes. Schottky diodes. This diode uses metal to semiconductor junction for rectification purpose instead of PN junction. Here the metal that is used is aluminum and semiconductor is the silicon. Therefore, a Schottky diode has aluminum silicon junction. Here, the free electrons in N material move towards this aluminum N junction and then travel through the metal to constitute the flow of forward current. Since here in the metal we don't have any holes, this means here the forward current is only due to the movement of electrons. As the metal has no holes, there is no shortage, no storage charge, and no reverse recovery time. This means that Schottky diode can switch off much faster than p-n junction diode. The reverse recovery time is around few nanoseconds. They have a low on state voltage drop of order 0.15 to 0.45, and have very low on low power on power, p on. They have typically typically available in voltage range in the from 20 to 50 to 200 volt. They are used in circuits having low output voltage like switched mode power supplies. Silicon carbide diodes. These are Schottky diodes constructed from silicon carbide. These have very low power loss. These have extremely fast switching behavior with ultra low reverse recovery time. These can operate at junction temperatures greater than 225 degrees Celsius. Their switching behavior is independent of on state forward current and temperature. These have much lower reverse leakage current than silicon Schottky diodes and high reverse voltage rating. These are very expensive as compared to silicon Schottky diodes. Different diode types include eggshell pack, plastic pack, stud type, this type. Here, this is the diode rectifier module, single phase diode bridge module, and this is the picture of the three phase diode bridge module.